The next intermolecular force we're going to be looking at is called dipole-dipole. And dipole-dipole forces occur between polar molecules. So it's going to be really important for you to be able to take that knowledge that you learned in Chapter 8 on how to figure out if a molecule is polar or nonpolar, because that's going to help you determine what type of intermolecular forces you have. So dipole-dipole is in polar molecules because they already have a dipole. So you can see there with HCl, chlorine is more electronegative, so it's pulling the electrons to itself, and so that side has a partial negative. Hydrogen side has a partial positive, and so it has that interaction there between the partial negative of one molecule and the partial positive of the other, and that's where the dipole-dipole forms. But remember, you can have multiple interactions going on, because we said that London dispersion forces are in everything. So this would also have London dispersion forces, but it also has dipole-dipole forces. And usually, if the molecule is the same size, then dipole-dipole forces are going to be stronger. And so that's going to determine its boiling point. So the strongest intermolecular force that's occurring between the molecules is the one that determines the properties. So, for boiling point, because the strongest intermolecular force has to be overcome in order for, an example of boiling point, in order for the liquid molecule to move from liquid phase to gas phase. So those stronger intermolecular forces determine those properties. Okay, so here's an example of, the difference between dipole-dipole and London dispersion forces. So here we have two molecules that weigh about the same, or exactly the same, 44 grams per mole, and the boiling points are different. So with propane, the CH3, CH2, CH3, the boiling point is 231 Kelvin. And then the other molecule, its boiling point is 294 Kelvin. Well, anytime I have a carbon-hydrogen chain, and that's it, just carbon and hydrogen, it is a nonpolar molecule. So the first one listed there is nonpolar, so all it has is dispersion forces. And then the other molecule has an oxygen in it, and it causes it to be polar. So this one has dipole-dipole forces. And since they're the exact same weight, the dipole-dipole force is much stronger. Now, if I had a molecule that was, a lot bigger than 44 grams per mole, like, the iodine, which was like 200 and something, then the London dispersion forces would be stronger. So the size of the molecule affects which intermolecular force is stronger there. The next one is called hydrogen bonding. And if we look at our graph, and we look at group 6, okay, so I'm not going to talk about water yet. Let's look at H2S. So that shows the boiling points of these molecules. So H2S has, pretty low boiling point, and then H2SE, as we go down the group, the molecule's getting bigger, so the boiling point's getting higher, and then H2TE, the molecule's even bigger, so the boiling point's getting higher. So those three right there follow the trend of what we've learned about the size of the molecule and the intermolecular forces. But water, H2O, oxygen's at the very top of that group. It's the smallest, but it has a much higher boiling point than the rest of them. And that's because we have hydrogen bonding occurring in H2O. So hydrogen bonding only takes place when we have a hydrogen covalently bonded to either nitrogen, oxygen, or fluorine. So just to give you some examples here. Okay, so we'll just start with water. Okay, so here's water. So we know that this is a covalent bond right here. right? That is an intramolecular bond or force. So that's not what we're talking about. That's not the hydrogen bonding, okay? The hydrogen bonding takes place if we had another water molecule come in. So this side is partially positive on this water molecule. This side is partially negative. And so this is where the interaction would take place. That right there, sorry, I didn't draw that very big. That's the hydrogen bonding. So it's not the covalent bond. It is the interaction between the molecules, but I have to have hydrogen covalently bonded to either oxygen, nitrogen, or fluorine for hydrogen bonding to occur. Okay, so that's really important. We also have, let's get rid of this here. Oh, that's taking forever. Another example would be NH3. Okay, so I have that hydrogen covalently bonded to nitrogen, but the hydrogen bonding takes place between the partial negative and the partial positive. So this would be the partial positive side. This is the partial negative side. And so there's the hydrogen bonding right there. Okay. But again, we have to have that hydrogen covalently bonded to nitrogen, oxygen, or fluorine. Okay, the reason they have such high boiling points is because nitrogen, oxygen, and fluorine are our most electronegative atoms. So they're able to pull hydrogen's one electron to themselves. Fluorine is the most electronegative atom there is. So that's what gives them these really strong intermolecular forces. Let's see here. As long as you have a hydrogen attached to the oxygen, you will have hydrogen bonding. So we have propanol as an example here. We have an OH group. So we will have hydrogen bonding taking place with that OH group. But we also have dipole-dipole going on. We have London dispersion forces. We have all three of those intermolecular forces in propanol. Okay, let's do this example. So we're going to figure out which of these molecules has hydrogen bonding. So I'm going to draw them for you. Okay, so the first one is ethane. So ethane, whoops, just looks like this. Okay, so remember I said if it has just carbon and hydrogen, it's nonpolar. And we don't have oxygen, nitrogen, or fluorine here. So there's no hydrogen bonding taking place. So we just have dispersion forces. So London dispersion. That's all we have here. So if the molecule is nonpolar, you'll only have London dispersion. Okay, the next one, hydrazine. We've got two nitrogens, and they both have two hydrogens attached. So here, because we have hydrogen covalently bonded to nitrogen, we do have hydrogen bonding. Okay, but that's not the only thing we have. We also have a polar molecule, so we're going to have dipole-dipole. And we're going to have London dispersion because we have London dispersion in everything. But the strongest of these three are going to be hydrogen bonding. So that's the intermolecular force we have to overcome to be able to, have those properties change. So if I'm going from a liquid to a gas, we have to overcome that hydrogen bonding. Okay, the next one is methyl fluoride. This one's actually kind of tricky. So looking at it, I've got hydrogen, I've got fluorine. Okay, yeah, that's hydrogen bonding. Well, when I draw it out, I get hydrogens attached to carbon, and I get fluorine attached to a carbon. So hydrogen is not covalently bonded to fluorine. So I actually do not have hydrogen bonding here. I do have dipole-dipole because it's a polar molecule, and I have London dispersion forces because that's in everything. So that one's kind of tricky. Okay, and then we also have hydrogen sulfide. So this one right here, okay, no hydrogen bonding. We do have London dispersion forces going on, and that's it. Those hydrogen sulfur bonds are nonpolar, so we just get dispersion forces.